Hello everyone. So we are going to solve question number 1 to 5 of set paper Pure Mathematics 2024. Okay, so this is about mathematical sciences. So the first question is the set given by 1 plus minus 1 raised to n where n belongs to n is. So firstly, this is the set that is given to us. So what are we going to do with it? We are going to solve it. For example, the first one, n belongs to a natural number. So the first number will be 1. So we are going to put it. And so 1 plus minus 1 will be equal to 0. Similarly, 1 plus minus 1 raised to 2 will be equal to 2. And then we can keep on doing it. 1 plus minus 1 raised to 3, that will be equal to 0. 1 plus minus 1 raised to 4, so that will be equal to 2. So the set will have only 0 and 2. So the right answer is going to be the option C. And then the next question is the number of non-empty subsets of X equal to this set containing only even integers. So this is the set given and we need to find the number of non-empty sets. So the formula for the number of non-empty sets is 2 raised to n minus 1. Okay, 2 raised to n minus 1. So this is the formula. So what are we going to do? Here we are asked to find only even integers. So among this X, let us take all the even integers and let it be equal to b. Like the set of even integers is equal to b. So it is only 2, 4 and 6. So when you have 2, 4 and 6, we can apply the formula 2 raised to n minus 1. Okay, 2 raised to n minus 1 is the formula for number of non-empty subsets of any set. Okay, so that will be equal to 2 raised to total number of elements are 3, 2 raised to 3 minus 1, that is equal to 7. So the right answer is going to be option A, 7. Then the next question is let k is a set, okay, be in r raised to n with the property that any real valued function, okay, in any real valued continuous function on k is bounded, then k is what among this? So whenever you have terms like continuous functions, bounded and something like this, then you must always remember Hein-Borel theorem. So the Hein-Borel theorem, what happens is the set K must be closed and bounded to be compact. Okay, remember the term compact. For example, if you take the general term, what does the word compact mean? Something that is so closed and tight and there are bounds to it. Like this circle itself is so compacted, I cannot go out of it. Okay, it has got a bound. Okay, and it is closed as well. There are no open spaces. So this circle somewhat looks like a compact one. So how can a set be compact? Only if it is closed and bounded. Okay, if set is not compact, this is the contrapositive of Hein-Borel theorem, and that is if the set is not compact, then there exists a continuous function that is not bounded or it is unbounded. Okay, now if every continuous function is bounded, then k must be compact. So here what are we given? Here in the question, you see the question says that let k be less than let k belong to Rn, and here the property is that any real valued continuous function on k is bounded. So if the function, okay, any real valued function, like if you pick up any real valued function, if that is bounded, then it has to be compact. Okay, and why did we take continuous function? It is because every continuous function on a compact set is bounded. Okay, so the answer is compact. Okay, now the next question, and that is suppose a bounded function 0, 1 to r is Riemann integrable, then which of the following is true? So there are many options given. First thing, let us know what is Riemann integrable, what is Lebesgue integrable, etc. So firstly, what is a bounded function? For a bounded function m on some interval, if there is a m greater than 0 such that the modulus of f of x is less than or equal to m, that is, it has some bound, that is a bounded function. And then Riemann integrable function means a Riemann integrable function is integrable on a, b if it is bounded, and also the set of points where it is discontinuous has measure 0. Okay, it has measure 0. Now what is measure 0? Measure 0 is equal to length 0. example, for example, okay, now a rational number from 0 to 1, okay, consider rational numbers from 0 to 1, okay. Now if we take the rational number from 0 to 1, there are infinitely many, okay, from a countable set, okay. Now see this Lebesgue integrable. Now what is a Lebesgue integrable function? So a Lebesgue integrable function is somewhat like Riemann function, but only the difference is that we take the mod of a function, okay. So if the mod of that function's integration is finite, and that is it is less than infinity, or you can say it is finite, then only it is Lebesgue integrable, okay. And remember this is very important, and this will be useful in all the examinations. Every Riemann integrable function is also Lebesgue integrable, and both in intervals are equal, or both integrals are equal. Yeah, right, or you will get confused. Yeah, so every Riemann integrable function is also Lebesgue integrable function, but vice versa need not be true. So now you can see this. The first thing is f is Lebesgue integrable. So I am given a function is Riemann integrable. So Riemann integrable implies it is Lebesgue. So this statement is true. So we have to find something that is not true. Next is Riemann integral of a function is same as Lebesgue integral, and it is always true, okay. See this, the first and the second is actually the same, the options mean the same. Next one is f is not Lebesgue integrable whenever f is discontinuous. Now we need to say this. See, we were told something here. See, it is the Riemann integrable function if it has any set of discontinuities, then it will have a measure 0. And here what it says that f is not Lebesgue integrable whenever f is discontinuous. So if f is discontinuous, it can be Lebesgue integrable only if it has a measure 0. But here it's directly given that if f is Lebesgue integrable, then always, okay, whenever f is discontinuous. So this will be our right option. Now we'll just see the D option, and that is mod of f is Lebesgue integrable, okay. Now if a function is Riemann integrable, it is Lebesgue integrable, and the mod of that function is also Lebesgue integrable, okay. It is, if f is integrable, it implies that mod of f is also integrable. If f is Riemann integrable, this mod of f is also Riemann integrable, okay. Now we can see the next one. Now a function is given from r to r, that is real number to real number. Then which of the following is not true? So this is very easy. If f is continuous, then mod f is continuous. Yes, it is true. And then if f is integrable, then mod f is integrable. Yes, it is again true. And if f is differentiable, then so is mod f. So this is not true, because see, for example, we know that x is integrable, okay, but if you go to see mod x, it is not x is differentiable, but if you see mod x, okay, it will not be differentiable, because at x equal to 0 it will have two values. It is minus for a function to be differentiable, it must have all its left hand limit equal to the right hand limit equal to limit at that point, okay, but here it won't be equal. So therefore we can say that the question here was which of the following is not true. So it will be C. And if f is bounded, obviously mod f is bounded, okay. And now we can even see this one. For n greater than or equal to 1, let an be the set of all irrational numbers in the interval 1 minus 1 upon n plus and 1 plus 1 upon n, okay. So which of the following is true? So here if you go to see the interval, it will be the numbers, they belong to natural number n greater than or equal to 1, okay. And here the interval will we have to take only the set of all irrational numbers in this set, okay. So it will again be infinitely many numbers will be there. So if I go to take the set, it will be 1 minus 1 upon 1, that is 0, comma 1 plus 1 upon 1, that is equal to 2, and then it will be 1 again 1 minus 1 upon 2, that is half, comma 1 plus 1 upon 3 by 2, etc. So among all these I have to take only the ones that are irrational. Okay, and if you take the irrational numbers, it will be somewhat like root 2, 1.000001, etc. So all those numbers will only converge to 1. Okay, so what can we say? Limit supremum of an is equal to 1. Okay, it will all converge to 1, but it will never be equal to 1. For example, the supremum here is equal to a. There is a door here, and everyone is moving towards the door. Okay, everybody is moving towards the door, but no one is crossing the door. So this door becomes the limit, and they all are converging towards the limit, but it's not equal to the limit. So it is equal to set 1. Thank you.